Understanding time complexity and big O notation at the core of algorithm efficiency lies the concept of time complexity, which quantifies how runtime increases with input size. Developers use big O notation to describe this relationship in abstract terms, focusing on worst-case scenarios. Big O simplifies comparisons between algorithms by ignoring constants and lower-order terms. For example, an algorithm with O, n superscript 2, complexity will struggle significantly as n grows compared to one with O, n log n. O, 1, constant time operations remain unaffected by input size, such as accessing an array element via index. O, log n, logarithmic growth occurs when each operation reduces the problem size by half, typical in binary search implementations. O, n, linear time means execution time scales proportionally with input size, seen in simple loops over arrays. Misunderstanding big O can lead to suboptimal choices, especially when dealing with nested loops or recursive functions that hide exponential behavior behind deceptively small inputs. Space complexity and memory optimization. If time complexity defines how fast an algorithm runs, space complexity determines its memory footprint. Efficient memory management prevents leaks, minimizes swapping, and ensures compatibility across devices. Some algorithms sacrifice space for time gains, like using hash tables for O, 1, lookups at the cost of higher memory consumption. Conversely, in-memory sorting may require auxiliary storage proportional to input size. Example, a quicksort implementation uses stack space for recursion, while merge sort requires temporary arrays equal to the original data size. Beyond raw numbers, spatial locality matters too. Caching-friendly algorithms benefit from CPU optimizations, making them faster even if their theoretical space complexity appears identical to others. Evaluating common algorithm categories. Different classes of problems demand distinct solution patterns. Sorting, searching, graph traversal, and dynamic programming each have canonical methods with well-established efficiency profiles. For instance, comparison-based sorts cannot be O, n log n, but non-comparison methods like counting sort achieve linear times under specific constraints. Choosing the right approach depends heavily on dataset characteristics. Sorting algorithms. Quick Select offers average O, n performance for finding kth smallest elements, outperforming full sorts in many cases. Graph traversal. Breadth-first search excels for shortest path problems in unweighted graphs, whereas Dijkstra's algorithm handles weighted edges efficiently with priority queues. Dynamic programming. Memoization trades memory for reduced computation, preventing redundant calculations in overlapping subproblems. Profiling tools help identify bottlenecks within these categories, revealing opportunities for hybrid approaches tailored to particular workloads. Optimization techniques for real-world applications. Real-world systems often involve complex interdependencies beyond textbook examples. Optimizations must consider hardware limitations, concurrency models, and external API latencies simultaneously. Caching frequently accessed results avoids recomputation, while parallel processing distributes workload across cores. However, thread synchronization overheads must balance against potential speedup gains. Data structure selection. Using balanced trees instead of linked lists improves lookup speeds, though insertion costs increase due to rebalancing requirements. Pipelining and lazy evaluation defer computations until absolutely necessary, reducing upfront processing demands during initialization phases. Case studies in algorithmic refinement. Many industry breakthroughs stem from rethinking existing solutions rather than inventing new ones. Netflix's recommendation engine evolved through iterative improvements in matrix factorization algorithms. Airlines optimize flight scheduling using constraint satisfaction techniques, dynamically adjusting routes based on real-time weather conditions and aircraft. Availability. Google PageRank. Originally implemented with distributed computing frameworks, it now leverages advanced mathematical approximations to handle web-scale data efficiently. These examples illustrate that algorithmic innovation rarely emerges overnight, It typically follows years of incremental refinement guided by empirical testing and domain expertise. Trade-offs between different approaches. No single metric governs optimal algorithm selection. Trade-offs exist between accuracy, latency, energy consumption, and maintainability across various application domains. Approximate versus exact solutions. Machine learning models sometimes prioritize faster inference times over perfect predictions, accepting minor errors for significant throughput improvements. Embedded systems might favor simpler algorithms with smaller footprints despite slightly worse asymptotic bounds, prioritizing reliability over marginal performance gains. Quantum computing introduces entirely new paradigms where traditional complexity measures lose relevance, requiring fresh perspectives on what constitutes efficient computation. Measuring actual performance through benchmarks. Theoretical analyses provide guidance, but benchmarking reveals true behavior under realistic workloads. Tools like Google Benchmark or JMH enable precise measurements across diverse environments. Micro-benchmarks isolate individual components, while macro-benchmarks simulate end-to-end system interactions. Both types inform decisions about whether observed improvements justify refactoring efforts. Statistical significance. Repeating tests multiple times helps distinguish genuine enhancements from random fluctuations caused by background processes or measurement noise. When comparing alternatives, ensure consistent test parameters, including data sizes, hardware configurations, and compiler settings, to avoid misleading conclusions. Future trends in algorithm development. Rapid advancements in AI or ML continue reshaping algorithm design landscapes. Neural networks now solve problems previously thought unsolvable analytically, challenging classical computational theory foundations. Specialized hardware architectures, from GPUs to TPUs, are pushing algorithm designers toward formats optimized for parallelism, vectorization, and memory bandwidth utilization. Eco-friendly computing. Green algorithms minimize carbon footprints by reducing both power consumption and physical infrastructure requirements through smarter resource allocation strategies. As global datasets grow exponentially, research focuses increasingly on approximate answers acceptable within tolerance margins rather than exact solutions constrained by computational limits. Conclusion. Mastering algorithm efficiency requires combining rigorous analysis with pragmatic experimentation. Understanding theoretical fundamentals provides direction, but real-world validation shapes effective implementations. By staying informed about emerging trends and continuously refining skills through hands-on practice, developers can consistently deliver high-performance solutions adaptable to evolving technological landscapes.